In this video, we're going to talk about self-organizing map or SOM. When we are talking about SOM, we're talking about a grid of neurons. So what it means, it is just like a piece of paper. It can be three-dimensional as well, but generally it is two-dimension. It is mostly seen as two-dimension. And they are like this. So this is a neuron and it is connected to another neuron and it is connected to another neuron. I'm gonna add two more here. And then after that you have another neuron here, another neuron here. So this is basically the shape of the grid of the neurons. And each one of these, like for example, if you have a data point here, so imagine this is a data point. I have this data point. And then this data point is going to be connected to each one of these neurons. So I'm just going to connect these bottom ones, but know that they are getting connected to all of the neurons. So that means, because it's going to be very complicated if I want to do all of them. So for example, this one is going to be connected and this one is going to be connected as well. They are going, each one of these data points is going to be connected to all of these neurons. So, and each one of these neurons have all of the dimensions. So for example, so we have lots of data points. Some of them are, actually, you know what? So we have lots of data points. These ones are green circles, and then we have black rectangles. So each one of them have different dimensions or different features. Like for example, the dimensions or features of this one is color, which is green. So I would say color is one dimension or one feature, and then shape of it is another dimension or another feature. And then we're going for the rectangle is the same thing, color and shape. So this color and shape, each one of these are going to have the same two dimension for all of them. So if you have, for example, a higher dimensional data, like for example, you have two different type of pictures. One is a picture of a dog and one is a picture of a cat, but you don't know which one is which because you don't have the labels, because this is unsupervised learning. What you do is you are going to take every pixel, and each one of those pixels are going to be a dimension or are going to be features. So both of them are referring to the same thing. And then all of those pixels are going to be sent to each one of these neurons. So each one of these neurons will get the complete data. It's not like they are getting, like one of them is going to represent the color and the other one is going to be representing the shape. All of them will get the same thing. So what is the point right now if all of them are getting all of the features? So another thing that these neurons do is that each one of them will give a weight to each one of these features. So each one of them will have different values, different weight for each one of these features. So they end up attracting a certain data point more than the others. Maybe this is not the best example for this. So for example, if I have numbers, first, just remember the structure is this. The structure is not the one that I'm going to create right now. The structure is this. You have a grid of either rectangle, square, or hexagon, whichever you think is going to best match your situation, and you can choose the number of neurons as well. And the number of neurons I'm going to show you, if you have less number of neurons, each one of them is going to be compact. So the difference between them is going to be higher. But when you're having more number of neurons, it's able to capture those details as well, because there are a lot of neurons that you can spread all of this information on. Okay, so For making this process easier, I'm going to have, for example, a few numbers here. I'm going to have 1, 2, 6, 8, 10. They don't have to be, let me just, for example, change this one to 12 so it doesn't look like that all of them are. So these are the data points that I have, okay? And then I want to cluster these numbers. These are all numbers that are mixed together, right? I don't know what the numbers are. I just know I have a data set of mix of numbers, and I want to spread them in, I want to be able to cluster them with SOM. And another thing to consider, SOM does not do hard clustering. So it doesn't say, okay, the number 1 and 2 are in one cluster, and then the number of 12 and 8 are in another cluster, or 12 and 10 are in another cluster, and then 8 is another cluster as well. It has a Gaussian type of structure. So initially I'm going to give different weights to each one of these. For example, I'm going to give 5 to this, I'm going to give 8 to this, I'm going to give 14 to this, I'm going to give 2, and I'm going to give, for example, 6. Okay? So these are initial weights, and I just have one dimension. I just have the numbers. It's just the difference between the numbers. So I'm going to bring the first number in. So my first data is 1. I'm going to find the best matching unit, or BMU, for this. The best matching unit for this one is this neuron. So I will consider this to be the cluster of number 1, okay? And then I'm going to change this to 1, but this 1 is going to affect 6 and 14. So I'm going to make 6 as a 2, and then I'm going to make 14 as a 3. Oh, maybe I should put it here. 2, and then 14, I'm going to change it to a 3. Okay, so the weights are reassigned based on the data point that came in. The neighborhoods got reassigned. I don't have the random one here anymore. And then, so this one is done. And then I'm going to 2, okay? For 2, I'm going here, and the best matching unit is going to be here. So I'm going to put 2 here. The neighboring is this one. It's pretty good. So I'm going to keep it the same way. There's no other neighbor, so it doesn't change anything. So that is 2. And then I'm going to have 12. It doesn't always mean that you have to have one less or more than the actual thing, the actual number that is there. It's depending on what type of distance you're using, it's going to be a different number. Depending on how many neurons you have and what is the shape of it, what is the shape of your grid, and what type of distance that you're using, these weights are going to be different. Also, you have multiple features. Here we just have one feature. So it will consider overall, and then based on that, it will come up with the weights. And then, so I have trained based on these 2, and then I have 12 here. So I'm going to take this 12 out, and I'm going to look here. So 8 is going to be closest to 12. So my BMU, or best matching unit, is going to be 8. Now I'm going to change this to 12. It doesn't have to match, especially because when you're reassigning, these numbers are going to be different. It just have to be the closest, the best match for this number. So I'm going to make it 12 for now. Okay, so now I have 12 here, and I have these 2 neighbors. But this neighbor is getting and is having effect based on this number as well. So I cannot increase it so much. It has to be compensating for this one as well. This 3 is going to, I'm going to assign something like 6. I think 6 is going to be fair. Let's do, I think 6 is fair. So I'm going to make this a 6. Okay. So now this one got updated, and then now I have an 8 here. My 8, I'm going to look at these, and the best one that is closest to 8 would be 6. So 8 is coming here. Now this number, this one, these two neighbors are gonna get affected by this, and also this one, this, like all of these 3. So now that I have 8, all of these 3 are going to be affected, but also they have some values there, so you cannot change them drastically. Okay, I would say I am going to change this one to 3. And then again, I'm just randomly changing this. I just look at it and I'm saying, okay, what number is fair? This number is going to compensate, for example, for this one, and this one, okay? I just want you to get the idea of what's happening here, but this is not the method that it is getting calculated. So now I changed that to 3. As you can see, 1 is going to have another BMU. So it's going to move to this one. The first neuron is able to represent 2 and 1. Now I have number 10. I'm going to look here and to see which one is the best representation. And as you can see, both 12 and 8 are the best representation, are the best BMU for 10. So I'm going to change this 5 to 8. Okay, so I have a weight of 12 here and I have a weight of 8 here. 10 can be represented by these two neurons equally. So in SOM, you have multiple ways to handle this problem. One of the ways is it will look at it, and the first one that it finds that is the best match is going to assign 10 to. So that way we're going to choose 8 for it. Another way is just going to randomly choose one of them. It's like flipping a coin, whichever comes out. It either comes 12 or 8, and it will assign it to that. And then another way for it is it will look at the neighbors. So let's add another one here. I'm going to make this neighbor as 1. Okay. Yes, so the neighbor for this is 1, and 1 is not close to 10, but 12 is very close to 10. So I'm going to choose this point to represent 10 here. So, because this neighbor was closer than the other one. So right now, as you can see, we have trained our neurons. Obviously, this is not good. First of all, I just had 1, 2, 3, 4, 5. I just had 5 data points that I was able to train this neuron, and the neuron is very small. So then when this one is assigned to 10, this one is going to change its weight to be closer to what 10 is, because the neighbors are going to change. This 8 can be something, I can change this 8 to 10 now. Okay, and then I have 12, 10. So now I can change this 1. I can actually change it drastically because I don't have any data point. This is just a random value that has been assigned initially. So there is nothing that holding me back from drastically change this value. So I'm going to change this to 9, the weight of this to 9. So it will create a Gaussian. You don't want it to be the same as this because you want a Gaussian. And so this is going to be the structure, right? This is not very well trained, but when you're looking at it, you will see that the similar data points in this way, even though I had one here and I had two here, at the beginning, this was all over the place, right? The weights were randomly assigned. But now that I have trained it on the data, when you're looking, you see that the bigger numbers are toward this end and the smaller numbers are toward this end, right? So this is the essence of what SOM does. There are multiple benefits to SOM. One, it can preserve the topology of the data. So it is able to put the points that are similar to each other closer together. So right now the bigger numbers are on this side and smaller numbers are on this side. And then another thing is, if you have multiple dimensions, when you're calculating the difference between, when you're calculating the distance between these data points in whatever space that they are in, like if you have a sparse data with huge amount of dimension, you're using cosine similarity, as I explained in the other videos, to find the distance between them, and then you're going to project it to a lower dimension. So as you remember, this was the same thing as dimensionality reduction, like PCA that we talked about. This will help us to visualize the data better. So SOM is a good system for visualizing the data in the lower dimension because we cannot see the fourth dimension. We are able to see the best representation of the data here since we are projecting it down. My neurons are being, my SOM is trained. Okay, so now I can give a random data, like for example, I can say, I'm giving you 5. So now when 5 comes in, I can assign it to one of these BMU because it is already trained. So I won't change the weights. I'm just gonna say where this 5 is going to fit the best. So right now this 5 is going to go here. It doesn't change any weights around it because this is just a random data. We already trained, the training is done. It's just from now on, whatever data comes in, it's just gonna say where they are gonna go. So for example, if you have 12 coming in, it's gonna go here. And then, okay, so now let's look at the dimensionality reduction of SOM. I have used this demonstration before. I'm going to show you. So for example, I have something here. It's like it's a glass, okay? And I can see data points all over here. Okay, because I'm looking at it from the top. So I see all of these data points close to each other because right now I'm just looking from that dimension. I'm not seeing the depth of it. I'm just seeing the 2 dimension. Okay, and then, but I am going to add another dimension, which is the depth. So now I have 3 dimensions and I can see some of these points are actually going to move, like one of them is going to be here, another one is going to be here. But when you're projecting it, when you're using SOM, it's going to, it doesn't care where, it does care actually, it does care where they are, but it will look at the, what is it called? Let's do a little bit more complicated here because we can at this point. And I'm going to change the color of these 2 and I'm going to make it green. Okay, and for example, actually, let me just bring them down, like very down here. So here. So these 2 points were originally here. How do I? These 2 points. And when I was looking at it from the top, it looked like they are there. But when I'm looking at it from its actual feature space, when I'm looking at it from its complete actual feature space, these 2 points are down here. So even though they look very close to each other, the actuality, these 2 points are farther away from all of these 3. Okay, so when we are going to represent that in SOM, what's going to happen is these uh, uh, these points are going to be very close. So like the black points, one is going to be here, one is going to be here, another one is going to be here. Or even if we have, yes, so it's going to be there. But these 2 data points, even though they look from the dimension that we can see, it looks like they are very close to each other. So because we cannot see higher dimension, like so right now you can see it, but like for example, if you have a 4th and 5th dimension and they look very close to each other, but they actually are not. You can't just remove few features, because this is going to happen. If you reduce few features in 2 dimension, you see that they're close to each other, but they are actually not close to each other. If you are using SOM, these 2 points are going to be all the way here. Even though you're looking at it and you say, well, these 2 points seem to be closer to these 2 points than this one to these 2 points, right? Why did it do this? Because you weren't seeing the other dimension. So yeah, this is basically what SOM is. It's a very powerful tool. That's a toy. It's a very powerful tool.